is Vivek Amin. This talk is an invited talk. Vivek is going to talk about electrical spin current generation in ferromagnets and antiferromagnets. He's an assistant professor in the Department of Physics at Indiana University, Purdue University, Indianapolis. He received his PhD from Texas A&M University, and currently his group investigates spin and associated magnetic moments of electrons to create new electronic or spintronic devices. With applications to magnetic memories and hardware implementations of artificial intelligence. So let me make you on the spotlight. Great, I think we can see you clearly and we can see your slides. So whenever you feel comfortable, you can start.
Okay, great. All right, well, thanks for the introduction. So I'm very happy to be here virtually to tell you a little bit about my recent work regarding electrical spin current generation in ferromagnets and antiferromagnets. So this is primary theoretical work, which was done in collaboration with Fei Shui, Paul Haney, and Mark Stiles at NIST. Okay, so before I begin, I'd like to tell you what you should take away from this talk. And the motivation of this research is really to find low power ways to write magnetic memories using spin currents and spin torques. But there are several challenges. First of all, spin torque writing is not yet low power enough for widespread adoption, and theory does not always match experiment, which makes it hard to optimize the effect. So what I'm going to tell you about today are relatively unexplored spin current generation mechanisms in ferromagnets and antiferromagnets, which might help optimize spin orbit torque. So here's the roadmap for my talk. I'm going to give an introduction on spin orbit torque, on symmetry constraints in magnetic materials, and different ways in which you can generate spin currents in magnetic materials. And then I'll talk about two different mechanisms of doing that. One, which we refer to as an intrinsic mechanism, and the other, which we call an extrinsic mechanism. Okay, so going back into the motivation of why we're looking at this, one of the main applications for this is magnetic memories, which offer several advantages. For instance, they're non-volatile, they retain data when they're off, or they're radiation hard, which is important for space and medical applications. And so what I'm showing here is a grossly oversimplified cartoon of what one such magnetic memory or a magnetic random access memory might look like. And so what you have here is this crossbar architecture of a bunch of magnetic bits, and each bit is a magnetic tunnel junction, which is two ferromagnets and a tunnel barrier sandwich in between. And depending on the configuration of the two magnetic layers, whether the magnetization is parallel or anti-parallel, you could call that a 1 or a 0. So this is a way of storing information. So what you need is a way to read and a way to write the information. Reading the information is relatively straightforward using the tunneling magnetoresistance. In other words, the electrical resistance of the parallel and anti-parallel configurations is different. And so you can use that to read out a 1 or a 0. The open challenge really is writing, and writing in an energy efficient way. And so the mechanism for writing, which we're going to focus on here, are spin torques. The original spin torque based mechanism for MRAM is a spin transfer torque. And so the idea behind that is if you run a strong enough current in one of these devices, you can change the configuration from parallel to anti-parallel and vice versa. And the way that works is when the current runs through the device, one layer, the fixed layer, becomes spin polarized and transfers its angular momentum to the free layer, thus flipping the bit. But what I'm going to focus on today are so-called spin orbit torques, which are a transfer of angular momentum from the crystal to the magnetization. So how does that work? Over here in this animation, I'm showing an example of one mechanism of a spin orbit torque, which comes from the spin Hall effect. And so the idea is that we have this non-magnetic layer underneath. We apply a voltage and run a current through it. And through various interactions that involve spin orbit coupling, we get a splitting of the charge current into a spin current that flows into the top ferromagnetic layer, deposits its angular momentum, exerting a torque, and can potentially flip the magnetization. So this is one example of a spin orbit torque. And if we look and sort of track the angular momentum flow in this, what we find is that this really starts from the atomic lattice. And through the Coulomb potential, angular momentum is transferred to the orbital moments, and through spin-orbit coupling, it's transferred to the carrier spins. So that's what you're seeing in this bottom non-magnetic layer, is a spin current that's generated literally by stealing angular momentum from the atomic lattice. That then flows into the ferromagnetic layer and dumps angular momentum into the magnetic order. So the reason why we care about this, why spin-orbit torque is promising, is because the atomic lattice, where the angular momentum comes from, is technically an infinite reservoir of angular momentum. So it holds a lot of promise that maybe we can exploit this to create something which is a very efficient device. Now, spin-orbit torque mechanisms are quite complicated and still emerging. So for instance, if we look at our device in the non-magnetic underlayer, we could have things like the spin Hall effect generate spin currents that are used for switching. We can also have orbital Hall effects, which can create currents of orbital angular momentum, which flow into the ferromagnet and then get converted via spin-orbit coupling and exert a torque on the ferromagnet. We can also have interfacial effects like the Rashba-Edelstein effect, and a generalization of this that takes into account spin-orbit scattering at the interface called interface-generated spin currents. So today what we're going to look at is the generation of spin currents within the ferromagnetic layer itself, which cannot technically exert a torque on the magnetization of the ferromagnetic layer unless it flows to the layer boundaries. And if there's some asymmetry between the layers, there could be a net torque which could be used to flip the magnetization. All right, so this is a fairly broad topic. How can we classify the different types of spin currents which are allowed in these materials? And so a very powerful way to do that is to consider symmetry. So the key message here is that symmetry constraints differ between different magnetic materials. So for instance, if you have more symmetry in a material, you have a more constrained spin current. If you have less symmetry, you have a less constrained spin current. So an example of a material which might have more symmetry is a non-magnetic material, which has no magnetic order, whereas a ferromagnet, which has a magnetic order, that magnetization breaks much more symmetries. So what does this mean in terms of the spin currents that are created in these devices? So what I've drawn here are a whole bunch of arrows. So let me walk you through this. The gold arrows represent either the charge current or up to assign the electric field. This is a thing that's generating the spin current. The squiggly arrows or wavy arrows represent the flow of spin, and the blue arrows represent the direction of spin. So with spin currents, you always have a flow direction and a spin direction. So if we look at the more symmetric devices, so for instance, the non-magnetic materials, symmetry constrains you quite tightly so that you can only have this configuration of spin current, where the charge, the spin flow, and the spin direction all have to be mutually orthogonal. So this is the orientation of the spin Hall effect, but it's really all that's allowed from symmetry in a bulk non-magnetic material. However, as we go to materials that have less symmetry, which have magnetic order, like a collinear antiferromagnet or a ferromagnet, if the magnetic order, so the magnetization or the Néel order parameter, is pointing along some arbitrary direction, then you're actually allowed the full spin current tensor. So you turn on an electric field and you can get all these orientations of spin current that result. However, it's useful for us to look at a case where the magnetic order is along a high symmetry direction. So in this case, I've put the magnetization or the Néel order parameter along, some high symmetry direction. And in this case, you find that things become a little bit more interesting. So with the non-magnet, you have this spin Hall orientation. With a collinear antiferromagnet, you might think that it would behave quite like the non-magnet because there's no net spin. However, this does break some symmetries. And so what you're left with is something like an anisotropic spin Hall effect. Whereas if you go to the case of a ferromagnet, you can have even more orientations of spin current. And the important message here is that the spin direction of these spin currents is not aligned with the magnetic order, which means if they flow to a layer boundary, they can exert a torque. And that's what we're after. Okay, so we've talked about the different types of mechanisms that are what symmetry allows for, but what are the different ways in which you can create these spin currents? So there are both extrinsic and intrinsic mechanisms which we can discuss. And it's important to be careful here because there isn't a universally agreed upon definition of what these things mean. So I'll tell you exactly what I mean in this talk. So if we consider at equilibrium a spin current which exists in a material, let's just call that Q, we could calculate that by summing over all of the electronic states, which are denoted by little I. And that's a sum of the occupation of that state times the spin current that is held by that state. So after we turn on an electric field, to linear order, we get two possible terms. Either we perturb the occupation of carriers, or we perturb the spin current, which is carried by that particular electronic state. And this is how we're classifying extrinsic or intrinsic contributions. So an example of an extrinsic contribution might come from impurity scattering, such as Mott scattering or skew scattering in a device, whereas intrinsic contributions come from the electric field perturbing the Hamiltonian and modifying the wave function to create a spin current. And so in this particular talk, I'm going to focus on two different ways in which that can happen theoretically. With extrinsic contributions, we're going to look at the electric field perturbing the occupation of carriers via the relaxation time approximation, whereas with intrinsic contributions, we're going to use the Kubo formula to calculate them. Okay, so let's look at intrinsic effects that can happen in ferromagnetic materials. So what we looked at were intrinsic spin currents that were generated by an electric field in iron, nickel, and cobalt. And what we found is that they have a relatively simple magnetization dependence. So if we look at the spin current, for instance, in BCC iron, what we're doing here is we've got a bulk or infinite sample of iron. Again, these are theoretical calculations. We turn on an electric field. We look at the spin current, which is flowing perpendicular to the electric field, but we calculate all spin directions which are allowed. And so we do this while varying the magnetization direction. So what I have over to the left is the different spin current orientations plotted as a function of magnetization direction. So all of these are flowing in the X direction, but the different curves represent the different spin directions which are allowed. And so technically, for an arbitrary direction of magnetization, we can have any orientation of spin current that's allowed. But what we find is something that looks like it has a relatively simple sinusoidal dependence. So despite the fact that symmetry allows for all of these unique spin currents, it seems that the answer is a bit simpler in transition metal ferromagnets. And so we can fit these curves to a relatively simple formula in which we have a contribution that doesn't seem to depend on the magnetization direction, which we'll call the spin Hall effect for historical reasons, and a contribution which we call the spin anomalous Hall contribution, which has this dependence on the magnetization direction. All right, so what I want to do now is focus on the spin anomalous Hall contribution, which is interesting because it depends on the direction of the magnetization. And so why do we call it the spin anomalous Hall effect? That's because at first glance, it kind of looks like it's a spin polarized version of the anomalous Hall effect. So if we turn on an electric field in a ferromagnet, we know we get a Hall current from the anomalous Hall effect. And since charge currents are spin polarized in ferromagnets, you would expect that anomalous Hall current to be spin polarized. However, what's interesting about what we've calculated here is this is really a generalization on that idea. It's not exactly the same thing as a spin polarized anomalous Hall effect. It just has the same dependence on magnetization direction. And the way that we can see that is if we look, for instance, at cobalt with the electric field along a particular high symmetry direction. If we calculate the anomalous Hall effect and we calculate what we're calling the spin anomalous Hall effect fitted to these curves, if the spin anomalous Hall effect was really a spin polarized version of this current from the anomalous Hall effect, then it should be the conductivity from the anomalous Hall effect times the polarization of the ferromagnet, which it's not. In fact, it's behaving as if the polarization is much greater than 1, which is impossible. And so really what we're calculating here are all the symmetry allowed spin currents which are allowed in ferromagnets. And in some cases, the spin version can actually be stronger than the corresponding charge version. Okay, so we talked about the theory of creating spin currents in ferromagnets using this so-called intrinsic mechanism. But what about experimental evidence of the existence of these spin currents? And so we were involved in a project which looked at the spin currents that were generated in a 32 nanometer thick slab of permalloy. And the idea was that if we run a current through this permalloy with the magnetization, say in a direction which is opposite to the electric field, and if in fact we do get spin currents that are flowing in a perpendicular direction, where the spin direction is not aligned with the magnetization, then those spin currents should flow to the layer boundaries and exert a torque. So sort of bend the magnetization, in this case, out of the layer boundary plane. And so that's exactly what we looked at using polar MOKE to measure the deviation in the magnetization of the layer boundaries. So this sort of effect can't exert a net torque on the ferromagnet, but it will exert equal and opposite torques at the layer boundaries. And so what we found as a lower bound estimate was a spin Hall conductivity of about 1,000 inverse ohm inverse centimeters, which is comparable to the spin Hall effect in platinum. And so this is evidence that by turning on an electric field in a ferromagnet, it will exert a torque on itself, which can be seen at the layer boundaries. So we also are interested in antiferromagnetic materials. And so in this case, what we're interested is looking at the low symmetry in antiferromagnets and what types of spin currents are generated in those particular materials. So this is part of a theory experimental collaboration with the authors below. Here, I'm going to focus just on the theoretical part of this project. And so what we were looking at is iron rhodium in the antiferromagnetic phase. And the way our samples were oriented, what we believe is that the nail order is 45 degrees from the direction of the electric field. So we have an electric field here along the direction X, and the nail order parameter would be along this X prime axis. And what we're interested in is the spin currents which flow here out of the screen or in the Z direction. And the generation of these spin currents and then what torques they can exert on a ferromagnetic layer, which is on top of this antiferromagnetic layer. And so what we did from a theoretical perspective is calculate the spin currents which are generated using the Kubo formula in iron rhodium. And as I mentioned before, because of the symmetry broken by the nail order parameter, you can actually have two different values of, or two different unique spin currents that exist in this sample. So here for a charge flow direction along X and a spin flow direction out of the plane of this drawing, we can have a spin direction that is a component that is both along the nail order parameter and perpendicular to it here in this Y prime direction. And so these calculations show that those two different spin currents are clearly different. And using spin torque ferromagnetic resonance, we can find signatures of these two different spin torques. All right, so in the last part of this talk, I will talk about extrinsic effects, in which case the electric field induces scattering, which leads to the formulation of spin currents. All right, so just to go back before to the ways in which we can generate a spin current. If we turn on an electric field, as I mentioned, there's two ways that the electric field can perturb the expression for the spin current. So with extrinsic effects, we're focused on the electric field perturbing the occupation of carriers, but leaving the spin current that is carried by the electronic states alone. So in this particular case, what we assumed is by turning on an electric field, we get a non-equilibrium occupation of carriers, which can be modeled by the relaxation time approximation. So this is the same physics that gives you the Drude model. And so what you have here is a perturbation of the occupation of carriers, which is proportional to the group velocity of the electronic states. So we can find the group velocity through first principles calculations and the eigenstate spin current as well. So this is a relatively straightforward calculation of a spin current that can be generated in a ferromagnetic material. All right, so here are the results of this calculation, which we refer to as a spin planar Hall effect, and I'll explain where that name comes from in a second. So what we found again, we're turning on an electric field. We're looking at a spin current generated in the ferromagnet via this extrinsic mechanism, which is flowing perpendicular to the electric field. And as we move the magnetization around, we want to calculate all allowed spin directions of that spin current. And to simplify things, we've taken these spin currents and projected them along a basis where one direction is along the magnetization itself, and the other direction follows this sort of strange expression. And these end up being the two non-zero components of the spin current. So the first spin current, again, which has a spin direction along the magnetization, has a dependence that looks like this. We've also calculated the charge current, and you can see that the spin current where the spins are polarized along the magnetization looks like the charge current up to a sign. And then we have this odd spin current where the spin direction, again, is perpendicular to the magnetization. So this is something that can exert a torque on the magnetization at the layer boundaries. So why do we call this the spin planar Hall effect, or what do we mean by that sort of expression? Well, the charge current that we're calculating here is the planar Hall effect, right? So this is a Hall effect that arises from the anisotropic magnetoresistance in ferromagnetic materials. It's an effect that wants to be non-zero only when the magnetization is at some arbitrary angle between your electric field and the direction of flow. And so this is why you get an effect that's non-zero, which is a maximum around 45 degrees in this ZX plane. So again, since charge currents are spin polarized in ferromagnets, we expect there to be a corresponding spin current where the spin direction of the spin current is polarized along the magnetization, and that's that gold curve that we get here. But again, like our discussion about the spin anomalous Hall effect before, this spin planar Hall effect is not equal to the polarization times the planar Hall effect. In fact, it's a little bit bigger than the ordinary charge planar Hall effect. So this isn't just a spin polarized version of the planar Hall effect. It has the same magnetization dependence, but because we're calculating the full spin current, there are other contributions that are allowed by symmetry, which just aren't captured by that description. But again, what's probably most interesting is this green curve, which is the spin current that has a spin direction which is transverse to the magnetization. That's the spin current which can then flow to the layer boundaries and exert a torque on the magnetization. And so here we're just referring to all of the spin-dependent generalizations of the charge planar Hall effect as the spin planar Hall effect. And so for earlier results, you can look at a paper which I was involved in looking at interface generated spin currents, in which we found this type of spin planar Hall effect in cobalt using a tight binding model. Also, you can look at another effect called the magnetic spin Hall effect, which is very closely related in origin to the spin planar Hall effect. Okay, so with that, here are my conclusions. So electrically generated spin currents in ferromagnets and antiferromagnets are comparable to the spin Hall effect in platinum. They have spin directions which are both transverse and parallel to the magnetic order. So the transverse spin directions can then exert torques on the magnetic order at the layer boundaries. These spin currents are not simply related to charge-based Hall effects. So if there is a charge-based Hall effect in a ferromagnetic material, these are not just the spin polarized versions of them. Symmetry allows for different contributions, different orientations that I've discussed in this talk. And experiments suggest that these spin currents can influence magnetization dynamics in single and multi-layer systems. So I'm done with plenty of time to spare, and I'm happy to answer any questions that you have at this time. Thanks.
That was a great talk. Thanks a lot. And thanks for being on time. So we are open for discussions. You can, as usual, raise your hand and we will unmute you, or you can also write in the chat. So David Smith, you can.
Hey, Vivek. Thanks for the nice talk. Question for you, when you were talking about the planar spin Hall effect, you mentioned that there is a spin current that would be, this one. Mm-hmm. So that would be transverse to the magnetization. Is it possible for that spin current to drive precession or switch the ferromagnet at all?
Yeah, so it's possible if there's some asymmetry that's introduced in the system. So if you just had a symmetric ferromagnetic layer, you would get torques potentially at the layer boundaries, but they'd be equal and opposite. So they'd cancel out. So you wouldn't see any net effect on the magnetization. But if there was some asymmetry introduced in the system, which is just a way of introducing inversion symmetry breaking, then you can get a net torque. And so potentially you could see an effect. Does that answer your question?
Don't see David right now, but yeah. Oh yeah, so he replied on the chat, it does, yes.
Okay.
So do we have another question? I have a quick one, which is more general to what you have been discussing. So I do understand that you want to generate a spin current, but as you know, irrespectively of the mechanism, the way this current will propagate inside the magnet depends on probably the damping, right? So you can have an exponential decay of the spin current from the interface that you generated. And you talked about ferromagnet, antiferromagnets, but I was wondering whether it's of any relevance to consider, for example, a material that doesn't have order and see how a spin current will propagate, like a frustrated magnet or a quantum magnet.
Right. Okay, so addressing the first question, so there's obviously different things that can affect the generation of spin currents and how they propagate. So probably one of the more relevant ones is dephasing, right? So if you inject a spin current which is not aligned with the magnetic order, it will dephase and cause a torque. So if you generate a spin current that's inside the magnetic material and the spin direction is transverse to the magnetization, it's logical to assume you'd have some dephasing and it wouldn't survive, right? It would decay, some power law or something like that. But the kind of surprising thing about this, maybe it's not so surprising, is that symmetry allows for these spin currents to exist. So in this particular case, when I talk about these spin currents, so for instance, the one in the green curve, right? Say the magnetization is along Z, you can work that out. That will be, a spin direction that, I believe is along X, right? So in that particular case, you have a spin current with a spin direction along X, but you have a spin accumulation that's still along Z, which is a little hard to wrap, it was at least hard to wrap my head around. But the idea is that you have a spin accumulation that's aligned with the magnetization. So there is no torque, there's no dephasing, and yet the spin current itself has a spin direction along Z. So it can only exert a torque at the layer boundary. So sort of to answer your question, depending on the mechanism and how it's created, it's possible for it not to dephase, it just to exist in the, the magnetic system and only exert a torque at the layer boundaries. If it comes from an extrinsic mechanism, from impurity scattering or something like that, where, it rotates around a spin orbit field as it's scattering, then it's possible that dephasing could be important and you could have those types of effects. So it's a great question. We actually don't know how these spin currents propagate. That's an active area of research. And you had a second question, but I've forgotten it.
So do not consider something beyond an ordered magnet. So not ferromagnet or antiferromagnet, but go in materials like frustrated magnets.
Sure, yeah. No, so that's not something that, I've looked into in particular. I think that depends on, sort of the domain structure and whether or not you could have pockets, in which you have certain spin currents that are created, but whether or not they would survive or how that would look kind of depends on the overall symmetry of the system.
So, Luis?
Okay, hello Vivek, thank you for the really nice talk. I have a question about the material you mentioned, iron rhodium. Do you have some experimental results on that?
Yeah, let me go over there. Yeah, so this is part of an experiment theory collaboration. I've just shown you the theoretical results here. I don't have the experimental results to show, but essentially the system is iron rhodium with, I believe, permalloy on top. And the idea was to see what the spin torques on the ferromagnetic material look like with potentially iron rhodium as a source of a spin current.
Okay. Okay. Are you considering variation in temperature, maybe to study the transition of the iron rhodium?
Yeah, so yes, right. So we looked at this in the antiferromagnetic phase. And actually what we found was quite interesting. I mean, if you extract the torques from the SDFMR measurements, you actually find a spin torque efficiency that's much greater than what we've calculated theoretically. So that's a bit of a puzzle. You know, at least usually it seems to be the other way around, but in this case, the experimental results seem to be much more strong. So it's possible there are other mechanisms at play.
Okay. Okay.
So Ruiha?
Yes. Hi. I have a question on the spin anomalous Hall effect. Like I was wondering what kind of symmetries do you need to achieve this magnetization dependence? Is there a minimal set of symmetries that you need?
Yeah, that's a good question. You know, in this case, I haven't done an extensive analysis of, you know, if the crystal symmetry becomes more unique, you know, what's going to happen in that particular case. I mean, you know, there are lots of studies in transition metal dichalcogenides and other things that break symmetry where you can have sort of new and exotic spin currents. But, you know, in this particular case, we're just looking at, you know, standard transition metal ferromagnets. So these are things that have, you know, the boring symmetries that you normally associate with crystals, and yet you can still see these things because of the magnetization, right? If the magnetization is not along a high symmetry axis, it breaks all symmetries. And so all spin currents are allowed. And that's kind of what we were after, is trying to understand what the dependence of those spin currents was.
Thank you.
Golem?
Maybe mic's off.
Hi.
Yes, we can hear you.
Yeah, I was having it hard to unmute my button. Yeah. So yeah, it was a great talk. So I have a general question, like when you were showing the animation in the first slide, I think, like this spin current is basically propagated in the ferromagnetic metal, right? So my question is like, I mean, is it propagated throughout the whole sample of the magnetic layer, or it is a like interfacial thing? I mean, the role of the thickness of the magnetic layer, basically, how?
Again, it's a great question, and I don't have a good answer for you, right? This is something that we're actively exploring. Right now, what we're looking at are bulk materials, right? So in this case, it's an infinite material, and we just want to know, how is a spin current generated in this material, right? The next phase in our research is to look at finite systems and actually look at the torques which are generated and compare those to the spin currents in bulk systems and see if there's a correlation or if there's something else that's at work. So, you know, to answer your question, the spin currents can be generated in the bulk and they can propagate through the ferromagnetic material. There's no reason, you know, for that not to happen. But the torque will happen at the interface or at an area where there's strong inversion symmetry breaking. So it's sort of both, I guess. You know, the torque happens at the interface, but the spin current can be generated in the bulk.
Okay, thank you very much.
We have one more question on the chat. Regarding NM, do you mean normal metal or metal with spin orbit coupling such as tantalum?
Yeah, that's what we mean. Tantalum or platinum, or, you know, anything with sufficient spin orbit coupling.
I think, yeah, we have some time. We still have some time, so yeah, let's go ahead.
Okay, Vivek, I have another question. So if you are planning to use the iron rhodium as a spin current injector, have you characterized the spin efficiency, the spin conversion efficiency in iron rhodium already?
Yeah, so that's what the experimental results were trying to measure. And again, what we found was something that was, almost an order of magnitude greater than what the theoretical calculations predicted. So here you've got something, I don't remember the exact numbers, I can get those for you later, but here we have, results around, 100 to 200 inverse centimeters, and these results were significantly greater, order of magnitude greater than this. So we're not quite sure why or what is causing such a strong spin torque efficiency. So if this is playing a role, either we're grossly underestimating it, or there are other effects at play.
Okay, thanks Vivek, again for your talk.
Yeah.
So we do have some time for a quick question. Let's see. If not, let's thank Vivek again. That was a great talk. Thanks for sticking around and answering all the questions. Oh, we have one more. So I don't know if Carlos, if you want to, I'm sorry if you want to do it. Yeah.
Yes, sorry, I arrived late. Hi, Vivek. I just concerning this point. So in iron rhodium, where is the origin of the spin-orbit coupling in this compound?
Sorry, could you speak up? I can't hear you.
Yeah, in the iron rhodium, where is the spin-orbit coupling origin? What is the source of the spin-orbit coupling iron rhodium compound?
What is the source of the spin-orbit coupling?
Yeah, in iron rhodium, I mean, it's because iron rhodium, 3D of iron, or do you have a global an idea of the origin of the spin-orbit coupling, if there is any in iron rhodium?
Right. I haven't looked at splitting or anything of an estimate of the spin-orbit coupling. I mean, technically it's embedded in my calculations, but it's just spin-orbit coupling that's coming from the constituent elements. So it's not something expected huge, but that's where it's coming from.
Great, thank you. So currently we do have half an hour break, which is not really a break. We have the beginning of the poster session. So we do encourage people to move there in Gather Town. I'm going to post here the link, so you can find it and go there. We thank Vivek again for a great talk. And for the whole discussion that followed. So the next session will be moderated by Luis Avilés Felix from National Scientific and Technical Research Council, together with Cheng Shang Jason Xu from Berkeley. I'm sorry if I mispronounce your names. Yeah, so in the meantime, people can follow the link and we can meet on Gather Town for the poster session. Thanks again, Vivek.
Okay, thanks.